after the cookie time, so I hope you're all energized by chocolate and sugar and things like that, and coffee for some. So today we have an external visitor, Marc Gieles from the University of Barcelona. He has a very long CV, and Uk knows everything about Marc, so I will hand the mic over to Uk.
I hope not.
Well, the CV is not that long, it's on that small piece of paper. But I know Marc for a long time, and if you join for dinner, I have an entire list of interesting stories that I can tell about Marc, but that's for dinner over wine and some good food. All right, so Marc obtained his PhD at Utrecht in 2006, so not even 20 years ago. Some are not in that situation anymore. After that, he moved to Chile as an ESO fellow, and that's where I met him. Stayed there for 3 years, then moved back to the UK as a Royal University fellow in Cambridge. Then got a big bag of money, 2013, an ERC, and you took it to create a new group at Surrey, where you stayed for 5 years, and then again a new group in Barcelona for the last 8 years. So I think it's time to move, and maybe you can come to Leuven someplace to create a new group here. Anyway, Marc is working on the stellar dynamics, multi-body dynamics and body dynamics on different kind of objects. Today we'll talk about a globular cluster. There's also something interesting is that Marc is an editor at the monthly notices. So if you have a paper that you have troubles to get accepted, you can be nice with Marc. All right. Thanks, Marc, for visiting us today and tomorrow. And then the floor is yours for about an hour. So.
Thank you. Right, so good morning, everybody. I hope I stay awake. I had a very early flight this morning, so please shake me a little bit if I stop speaking. So today I want to present, first of all, introduce a problem that has been out there for half a century, and a possible solution, and some predictions that come with this possible solution. So before I go into all the details of this long title, is there who is aware of the multiple populations problem in globular clusters? 1, 2, 3, 4. Okay, 50%. All right, I'll pitch it a bit like that. So the first figure here is an image made by the brother of Julia Bodensteiner, Fabian, who makes beautiful artist impressions of what we think is going on. So it shows a globular cluster. It's omega Sen in the background, heavily massacred by his rendering program. And we think that when this cluster was very young, there were stars that were well beyond the masses that we see today. And I'll try to convince you why we think that is. It's not just an idea. We have good solid reasons to believe that. And if that's true, then they may have left behind black holes of a very interesting, in a particular mass range. And that's the final part of my talk. So let me first introduce the problem to the 50% of the audience that's not yet familiar with this. So this problem is, as I said, a problem since the early 70s. It was noted that globular clusters, as you see here, 2 beautiful examples. These are very dense stellar systems of a few parsec in diameter, maybe 100,000 to 1,000,000 stars in there. They're very old, so as old as the universe within the error bars of age determinations. And if you would pick 2 clusters with the same age and the same metallicity, the people noted that there were some differences in the stellar populations that couldn't be explained by just metallicity. Now, I like to say that in this image you can actually see it, but I believe that is just a RGB relative color contrast idea. But if you squint a little bit, you can see a little bit more blue stars here. And as I said, I think that's just a coincidence. But if you make the CMD of M3 and M13, you see that there's a bit more extended horizontal branch here on the right. And this was noted already by Sandage in the 70s, right? So the same age, the same metallicity. So why is that? Now, in the last 10 or 20 years, especially thanks to the Hubble Space Telescope, we have seen many more peculiarities that may or may not relate to this second parameter problem. The first one is the well-known photometric split in the main sequences. So we see, if we have very accurate, precise colors, we can see that there's a blue second and sometimes even a third main sequence. And this is not due to binaries, because the binaries are here on the right. They tend to make the stars redder if you have a companion. But we think it's due to an excess of helium. So there's a higher helium abundance in these stars, makes them slightly hotter, and this can also explain the horizontal branch. If you take spectroscopy of light elements, there's various flavors of this, but you can see very particular anti-correlation. So here you see individual stars in about 20 globular clusters. If you plot the oxygen versus sodium, it's a very big spread. If you would look at the iron abundance in every individual globular cluster, it's a very narrow delta function. So there's no spread in the heavy elements, but you see in these light elements very clear spread in abundances. Another one, this is the most famous one. It was noted actually first that there was a nitrogen spread in some narrowband filters in CN bandwidth. And more recently, people found that also magnesium and aluminium anticorrelate, but that's not true for every globular cluster. And this is an important ingredient in the story. So this magnesium-aluminium anticorrelation is there sometimes and sometimes not. And I believe that that's telling us something very interesting about the formation of the cluster. Now, this old problem has received renewed interest because now we can see, thanks to the James Webb Telescope, how galaxies form at high redshift. And when people say we see galaxy formation, I hear we see globular cluster formation, right? Because globular clusters are so massive and they form in a very short time that at this very early epoch, where we only see the brightest parts of the brightest galaxies, we see these starbursts where the most intense star formation occurs, right? So I believe that what you see at a redshift of 10, this is a famous example, this is 10.6 or 10.8, they rounded it up to 11, GNZ 11. This is most likely the first population 2 starburst in this galaxy, and I believe it's probably dominated by stars that end up in what we now see in globular clusters, right? Now, if you take this impressive spectra at this redshift, there's a clear excess of nitrogen in these galaxies, right? And it's, if you quantify that and compare it to the local star formation galaxies, so these are redshift 0-ish or 0 to 1, you can see that nitrogen over oxygen is almost 1 order of magnitude in excess, right? So this is in the entire galaxy, but this could still be, because at this redshift, the galaxy must have been really small, the first sites of star formation. Now, it happens a lot that you sit in a conference and people ask you, what do you work on, right? And I say, I work on a multiple population problem. Okay. And then very quickly people come with ideas to solve what you've been thinking about for 5 years, right? So, and this could be any other specialty. I took the cosmologist because I thought probably safe in this room, I don't know. Could have said massive star formation. So typical suggestions I get is, but maybe it's like mergers of clusters, right? So some clusters have high sodium, others have no, it doesn't work because the iron abundance is the same. How can 2 completely different sodium abundances magically give you the same iron? That cannot be, right? Maybe it's an age spread. No, you don't increase nitrogen or sodium with age. That's not it. What if stars rotate? No, can't do that. And what about internal mixing? No, you can't do it. So then always these conversations, they end somewhat disappointingly for the other side. And I say, no, it's the data really tell you you must burn hydrogen at very high temperatures. That explains all the abundances. And the question is, what does that, and how do you get that stuff into the low mass stars? That's the problem. So what do I mean with this hydrogen burning? Well, all these anticorrelations are the result of these reaction chains that happen while you burn hydrogen at increasingly high temperature, right? So we're all aware of the proton-proton cycle. That's what the sun mostly does. If you crank up the temperature a little bit, you start the CNO cycle, which is what almost every massive star does, but the sun does a little bit as well in the center. But if you go up in temperature, you start to ignite the other reaction chains that are mainly all catalysts in the process of turning hydrogen into helium, right? So, and what happens is what you probably know from the introduction of astronomy. Some of these reactions are fast, others are slow. So you get the pile up at the elements where reactions are slow, right? So in this case, that is nitrogen 14, and here it's sodium 23, and here it is aluminium 27. So that you get a lot of, and then you get less of the material that is capturing protons very quickly. So to remind us, the central temperature in the Sun is only 15 million Kelvin, and the stars in globular clusters are less massive than the Sun, right? So this is the mystery. Like, how can a star of 0.8 solar masses show an aluminium enhancement, right? It clearly cannot do it by itself. Now, then the anticorrelations, what I showed before was a compilation of all the clusters that Carretta had in a sample. But if you look at individual clusters and you compare them, so here you have a massive cluster and a lower mass cluster, doesn't really matter which one they are, and you compare these sequences, you can see that the shape of this sequence is slightly different, right? So here you have a little bit more oxygen depletion or less sodium enhancement than here. And if you look at nucleosynthesis calculations, that is actually what you expect for a higher temperature, right? So I showed before that neon sodium is active, but at different temperatures it works in different ways. I'll show that later in a bit more detail. So this is an indication that the temperatures were higher in the more massive clusters. Now, if you do this on a cluster by cluster basis, so now every dot is a globular cluster, so it's the average spread in the aluminium-magnesium anticorrelation. So as I said before, this one is a one that's not always there. So it's most prominent in the most metal-poor clusters and in the most massive clusters, right? So this we see always, but there's differences in the shape that indicate a temperature increase with mass and also metallicity. But magnesium-aluminium very clearly tells us more massive clusters and more metal-poor clusters, they had hotter polluters, right? So the temperature in whatever made this magnesium-aluminium anticorrelation was higher. Now, if you summarize 20 years of literature, you can roughly divide the proposals in two broad categories. There's a very large number of flavors and variations and details that have been proposed, and this list is very incomplete. But roughly speaking, and historically speaking, we started with trying to solve this with AGB stars, even though they're low mass, according to most of you in the room probably, but also to me, 5, 6, 4 solar mass. They have a stage where they undergo hot bottom burning, where you can reach temperatures that ignite almost all of these chains, right? So nucleosynthesis-wise, you can get these elements, but there's lots of details. And massive stars, of course, can do it, right? When they're on the main sequence, they can easily reach those temperatures. So I'm not going to, I used to have a few slides on all the problems with the AGB stars. I decided not to do that. If you want to know more, please ask me about it. I'm just going to try to convince you that this is a more promising route to explain it. It's the positive approach. Rather than bashing the AGB stars, I'm just going to sell the massive stars to the audience. So every model that tries to explain it doesn't only need to do the nucleosynthesis, but it also needs to make the material and get it into the low mass stars, right? So that's where the real challenge lies. So actually, there's one challenge also from the nucleosynthesis perspective, that if you look at the average helium spread, so this is again a collection of globular clusters, and each point in the histogram is one globular. The average helium spread is only 1 or 2%, right? So it's very small. So if you do this with a massive star, you need to do it very quickly, very early on. You cannot wait until the end of the main sequence, because then helium would be really high. The second challenge is that there's a mass budget problem, and I think actually the specific mass budget problem is the more interesting one, which is the mass of polluted material per unit of cluster mass. Because if you plot the fraction of stars that is polluted according to some criteria, like sodium enhanced more than a factor of whatever, then you can see that this increases with the mass of the cluster. So it's about 40% for low mass clusters, and it goes up to almost 80%, right? So the majority of stars in each globular cluster is weird and has received some material. It's not saying that the entire star was made out of the wind of some polluter, but it contained enough material to reach this criteria of being a polluted star. And as I said before, this correlation between, or the dependence of the temperature that we derive from the shape of the aluminium-magnesium anticorrelation with cluster mass and iron abundance is also not trivial, right? If your IMF is normal, why would the amount of material and the temperature depend on the cluster mass, for example. For iron, you could maybe see that more metal poor stars are hotter. There's some trend, but this trend is quite strong. You can't just explain it with that. So, okay, let's talk about massive stars. So we decided, like astronomers like to do, to make a new subcategory. So, but we thought it was good to have a name for each DEX in mass. And I followed somewhat Paul Crowther's attempt to do this a decade ago, but not quite. So you're all familiar with massive stars, which we use for the 10 to 100 solar mass stars that we're all familiar with and have observed. Very massive stars, we take the next decade. So there are a few known cases in resolved stellar populations, and there's extragalactic evidence that they are probably widespread in star-forming galaxies. And then we have extremely massive stars for 1,000 to 10,000, and then we reserved supermassive stars for the 10,000 and above, because that's what usually people use when they talk about IMBH or supermassive black hole seeds, right? So, and we haven't seen those, but I'm going to try and convince you that they must have been there. At least these, maybe these, not sure. So one of the reasons why I like the massive star solution to this problem is because they are far simpler. Not if you ask somebody like Pablo who tries to model them in detail. There's lots of complexities, and there's a lot of things we don't know. But there are simple scaling laws that on the main sequence you can basically link, for example, the mass to the central temperature. This depends a little bit, this linkage, on where you are in the evolutionary stage, but there's a very clear power law relation between mass and temperature. So if you correlate now these nucleosynthesis results to mass, you can see which of these chains correspond to which mass range, right? So the CNO cycle is always ignited, so that doesn't tell you anything about which mass to use. The neon-sodium cycle is also already active in low mass massive stars, so 10 solar mass stars. But as I said before, the magnesium-aluminium chain is activated at about 63 to 65 million Kelvin. It's not a hard onset, it is a gradual transition, but it tells you something, so that if you see this anti-correlation, it means that if there were ZAM stars, so early in the main sequence, and the reason why I want early in the main sequence is because of the low helium spread we've seen in the CMDs, right? So then this already tells you that you should be thinking about 1,000 solar masses or above. Now there's another chain. I won't say much about this, but if you care about K, potassium, I am very obsessed by potassium at the moment, then I'm very happy to say more about it. But potassium is extreme. I mean, it barely doesn't even fit here. You need 100 million Kelvin to, potassium spreads have been found, but I'm not saying much in this talk, but I'm happy to discuss. The other thing which is interesting at around 1,000 is that from the models that we have, and as I said, there's many things in the numerics of how do you model these stars that we're not certain, but they seem to be completely convective, right? So we know that the convective core grows if the star is more massive, but there is a mass at around 1,000 or 1,100 solar masses where the entire star basically becomes convective, right? And that's really great, because that means that everything that's made in the center reaches the surface very quickly, right? So later I'll talk about the winds. These stars must have immense winds. So we already see here like a very little opening to a solution, right? Because if you have a star that surface abundances are the same as in the center and has a strong wind, well, that's a nice way of making magnesium aluminium in the intra-cluster medium. So I think just by looking at stellar evolution and nucleosynthesis, you must be looking in this range, 60 to 70 million Kelvin. Some clusters don't have the magnesium aluminium anti-correlation, others do, so there must be a little bit on the left and a little bit on the right. Hand wavily, very roughly speaking, that tells you then 500 to 5,000 solar mass stars. Okay, so now I'm going to try and use all of these ingredients and build a globular cluster with a sort of formation model, and but this is very difficult, right? So people are trying very hard to form clusters with hydro simulations in a self-consistent cosmological background where you have radiation, ionization, feedback, gas inflows, the whole thing, within an expanding universe, right? So that's how I think about globular cluster formation. Like, it's future. We can't model that. It's very difficult. I would say it's impossible now. If you really want to form from brown dwarfs up to 10,000 solar mass stars in a cluster where you do everything self-consistent correctly without recipes, no, you can't, right? So I'm going to think about a blueprint for our children to work on in 100 years when they have the machinery to do that, right? So now, I was sitting on the other side of the table at one point, in my office actually. I arrived in Barcelona, and now I'm this guy asking the silly questions. So, and the next door neighbor was a star formation expert. So I said, oh, wow, you work on star formation? Yes, massive stars. Oh, wow, that's really interesting. I really like massive stars, but I don't know how they form. So I said, so how do they form? How does a massive star form? Is it like this core collapse idea that people talk about, or is it now this competitive accretion that is more popular and is definitely in the modeling, right? Like Bonnell and Bate. And he said, neither. They're both wrong. I have the solution. I know how they form. So this is Paolo Paduan, and he convinced me that his model of forming massive stars is very appealing, very simple, and very useful if you want to understand things that may have happened in a globular cluster. So let me try to step in his shoes and explain to you how his model works. So in his star formation model for massive stars, the supersonic turbulence in the cloud creates filaments that are converging not by gravity but just by inertial motion that they have from the turbulence in the cloud. That means that some of these filaments intersect, and at the point of intersection, a seed star forms and they start accreting. And it actually goes relatively slow. It goes on the dynamical time of the cloud, and that can, in the Milky Way, take 1 or 2 million years. So his current idea is that it takes quite long to form a massive star in the local universe. So then that gas starts accreting onto a disk, and the disk accretes onto the star, and then at some point, I mean, these are MHD simulations, but they don't resolve the actual individual star and the evolution of the star, right? So there's some magic happening between the disk and the accretion onto the star. But the neat thing about this model is that it behaves in a very simple way that you can scale. You can scale it to different environments. So, for example, one aspect of this is that if you look at how the stars grow in time, it's almost linear, right? So there's some variation. So these are individual stars that reach a similar mass of around 30 solar masses. And you can see that it's not competitive accretion. Competitive accretion is Bondi-Hoyle accretion. So m dot goes as m squared. So you should see a runaway growth of the mass. You don't see that. You see a very gradual linear. And the idea behind that is these are these inertial flows that don't feel the gravity. They just move at a constant velocity and they reach the star. And at some point the cloud is the crossing after the dynamical time of the cloud dissipates and is gone. Right? So clouds don't really exist for more than one crossing time. They're marginally bound structures that are temporarily there because of turbulence, but then after one crossing time they're gone. The other thing which is very nice, and this is what we use to scale up to the, so because these models cannot model the kind of environments we're interested in yet. They're small scale simulations. This is a box of 250 cubed parsecs in the Milky Way disk. And for about 100 million years, they form stars. And what is, I think, different about these models compared to the Bonnell and Bate competitive accretion is that it's not a simulation of a single cloud that forms a bunch of stars. It's an entire box with a reflective boundary condition that feeds the turbulence by the supernova that occur in the star formation simulation itself. Right? So it's the box remains turbulence because of the star formation that happens. So then if you look after, I think this is 50 million years, like you look at all the massive stars that have formed, how long it took, and as a function of their final mass, so when they were done accreting, you can see that they are all within a sort of envelope here, and there's a meaning to these edges here. So the top edge, the maximum time to form a star is basically the dynamical time of the cloud. Right? So there's no stars that take longer than one dynamical time. As I said before, then the cloud is gone, so all the accretion stops. And the fastest time, the minimum formation time, corresponds to the maximum accretion rate, which is a small number times the mass of the cloud over the dynamical time of the cloud. Right? It's 10 to the minus 3 within a factor of 2. And the average, and then where these lines intersect, that's essentially the most massive star you can form in that cloud. It's like a structure of gas. And that's approximately this number. So it's 10 to the minus 3 of the gas cloud, right? So if you have 100,000 solar mass cloud in the Milky Way, your most massive star would be 100 solar masses. Sort of works out. And the average, the fit to these data points here, is almost a beautiful square root relation, right? So more massive stars take longer to form, but they will start before the low mass stars and end as last, right? So that also intuitively makes some sort of sense. Now you can, because it's all driven by supersonic turbulence, which you can scale, you can now say, okay, what if the gas density was higher? Then this whole graph just goes down, right? So you can do everything faster and avoid that supernova become important while the stars are still forming by just increasing the gas density by a factor of 3 or 10. So that's what we did. We scaled this little Milky Way simulation box up to a molecular cloud in the early universe. And we said, what if the cloud was now not 100,000, but a few million solar masses? And what if the gas density was not 100 solar masses per square parsec, but 1,000? So it's not an extreme step. And actually, this number is consistent with what people see in ALMA observations of high redshift galaxies. Right, so then you find that the most massive star is 10,000 solar masses, not 100. And you can do that within 2 million years. So before any supernova take place, right? So now let's apply this to real cases. So if you say the most massive star is 0.1% of the mass of the gas cloud, and you say 10% of the gas cloud ends up in a cluster, then you have a relation for the most massive star as a function of the cluster mass, 1%. And if you then say, okay, do we know any objects in this regime? Well, we know in our Milky Way, the most massive stars are around 100 solar masses. So Westerlund 1, for example, NGC 3603, we know of some clusters that contain these, but these clusters are 10 to the 4 solar masses, right? In R136, in the Magellanic Clouds, we see 100,000 solar mass clusters. And this relation would predict 1,000 solar mass stars. We don't see 1,000 solar mass stars. We see 300, maybe 400, but it's close. And the difference might be due to winds, and I'll come back to that. And this relation then predicts that to form a 1 million solar mass cluster, you will get something like 10 to the 4, right? Now, this number is purely based on the inflow rates. I've ignored the winds, right? So you don't reach those masses because stellar winds will not allow you to go so high. But I'll do that. But just as a reminder, I showed that one of the properties of these multiple populations is that both the complexity but also the amount of the fraction of these polluted stars scales with the mass of the cluster. Well, this is a potential way of explaining that, right? You have just more of these stars and you have hotter stars, so you can explain both of these scaling by the simple assumption that, or the result, that the most massive star scales with the mass of the cluster. So here's what we think the IMF of a globular cluster may have looked like. So there were definitely very massive stars and probably also extremely massive stars and maybe even supermassive stars, right? So it just continues. So this slope is the minus 2.3 something. The Salpeter or Krupa slope is the result of turbulence, and that there's no reason why it's different at these masses than here between 10 and 100. So now, of course, these stars are more than just accreting seeds. They start to evolve at some point, and then they'll start to have a wind. And the wind will stop everything from reaching the most extreme masses. So this is a plot of one of Jörg Fink's group's papers. It's not really as a function of mass, but you can somewhat interpret the x-axis as mass. And this is the mass loss rate. The point of this figure is that there's a transition where as soon as winds become optically thick, so photons take multiple scatterings to get out, the wind mass loss rate goes up a lot. And there's multiple relations, and we use a fit to the mass where it goes as m squared. And this is important. So it's faster than linear with the mass. And there's a dependence on the metallicity, because if you have less iron, you don't push as easily the material out with the photons. So then what we did in our little toy model, we said, okay, now we have accretion, which is linear in time and depends as the square root of the mass, and winds depend as the square of the mass, and we just add them up, right? So the star starts growing, and if you're a metal-rich star, well, the growth stops around here because of the winds, and if you're a more metal-poor star, your growth stops about there. Accretion rate is the same, but the winds will allow you to grow further. Now this is actually really important because this also shows that more massive stars are expected at lower metallicity, right? Just that's purely due to winds. And the other nice consequence of this is that even though the mass loss rate of low metallicity stars is lower, because they grow to higher masses, the actual mass loss rate will eventually reach the accretion rate. Right? So the amount of material that you make in a low metallicity cluster isn't that much less than in a high metallicity cluster, because the mass loss rates are somewhat similar. And that's because the masses are higher. Right? So there's a mass metallicity anti-correlation. And that's important because Jorik Vink has been trying or discussing the multiple populations, and he always points out, like, well, the low metallicity stars are a problem because we don't make enough material relative to the high metallicity stars. But that's when you look at a given mass. If you allow for the low metallicity clusters to grow to higher masses, you can make about the same amount. It's a bit less, but it's comparable. It's not the z to the 0.6 that you might naively expect from this scaling. So this is the second thing I wanted to remind myself of, is that this explains the scaling with metallicity. Higher temperatures in more metal-poor clusters are not only because stars are hotter at low metallicity, which they are, it works in the same direction, but it's a smaller effect, but you have a significantly higher mass at low metallicities. So now we can build a simple model with 3 parameters for the globular cluster, right? So one is the gas cloud mass, which sets the most massive star mass, or the theoretically most massive star mass if you ignore the winds, right? So the highest accretion rate. The surface density tells you basically how quickly it happens, how fast you form the cluster, and then the metallicity sets the winds, which sets indirectly the most massive star mass, right? And then we can basically write down what the mass of a star is as a function of time and its final mass, and then the gas density and the metallicity. And this allows us to evolve the IMF, to form the IMF. But there's no real IMF, it is always evolving, right? So this is the early IMF, or the early mass function, the EMF. So everything above 1 solar mass, we say everything below 1 solar mass doesn't form like this. It forms through fragmentation, the Shu classical way, continuously. So while you're forming the massive stars, which takes about 2 million years, you continuously form low mass stars as well. And here on the top we show just the mass function evolving, so it is somewhat salpeter-like. These are still heavily accreting, so it's steeper, and then eventually they're all salpeter, but here you can see the effect of the winds, right? So it's not continuing until here, but there's a bump of stars here, which is because of winds. And here we look at the rates, so this is the accretion rate, and this is the wind mass loss rate. We ignore the stars below 100. We say everything above 100 is optically thick and relevant, and everything below 100 is irrelevant. It's not quite true, but it's much less. So you can see that most of the wind, because of this m² relation, most of the winds comes from the very rare, most massive stars, right? So all of the material is most of the material is dominated by 1,000 and above solar mass stars. So the most massive ones are the ones where accretion and winds have become somewhat similar, and the phase in which their winds are really strong is during the accretion still. So here I suspect people are starting to worry about some complexities about winds of accreting stars. I'm very happy to talk about that, but I'm sure that that's future work. So then we need to label the wind with abundances, right? We need to tell the star that releases some material what the abundances are, and we do this by using the fact that the stars are convective. So at a given time, you know the mass of the star and the helium abundance, so you know the temperature. So then with the temperature, you just look up the nucleosynthesis tables of Pranzos, for example, but there's others. You can also run your own. And then you can say at any given time, what is helium, what is sodium, what's oxygen, what's magnesium, aluminium, and etc. I show here the ones that are enhanced, but we also do it for oxygen and magnesium, which are depleted. So first, helium. So this is what the helium abundance would be if you would just say the helium abundance goes up on the nuclear time, right? So then these stars are the oldest. This is an average helium abundance. So here are stars that are just forming, and there are stars that are already done. But these are the stars that are the furthest in their main sequence. So you expect quite high helium abundances. But because you continuously accrete material with pristine helium abundance, you actually suppress the helium abundance, and the highest mass stars are the ones with the lowest helium, which is also good because we needed to have low helium abundance in the final globular cluster. Now here you see the evolution of sodium and aluminium and nitrogen. Nitrogen is the simple one. Sodium and aluminium have some time dependence. And this is a tricky one. We need to then say what happens to these winds. How do they end up in the low mass stars? And we make a sort of assumption about dilution of these winds by the material that is still accreting onto the globular cluster, right? And this is very uncertain, and here we can probably do very different things, but we choose to do something very simple. So we said the average accretion rate of material onto the cluster is given by the total star formation rate, and then we say the winds are diluted by this ratio. So that means that the winds of the massive stars are diluted less than the winds of the lower mass stars, right? So these lead to the most extreme observed abundances, and these are the ones that are closest to the pristine abundances. I hope I explained this well. This is a little bit tricky. So then what we get is the evolution of the abundances of a gas that is forming the low mass stars, right? So again, there's a magic step here where we convert gas into stars. If you believe me here, then this is what the abundances would be of the newly forming low mass stars, right? That are forming out of this mixture of pristine gas that flows in and winds that are coming in. So then we do that for helium, and then the main culprits here. So in the dashed lines, you first see the material that comes out of the stars. So this is the undiluted material, and then we mix it with pristine material. And this is, as you can see, changes a lot because it's about factor of 10, right? So you start with 1 unit of stellar winds, and then you, on average, throw about 10 units of normal gas, with pristine abundances. So what you see here is that you get 2 peaks. So you have a peak very close to the undiluted material and a peak close to the pristine material. And this is due to the fact that we have this pileup of stars here in the mass function that leads to a very pronounced abundance trend here. So these stars dominated over these stars, and then we spread them out with this dilution, and that makes it even further broader, that distribution. And it's an important ingredient because here you see it's a complicated color that the labels don't reflect what it is, but it's essentially a multi-color diagram. So there's 3 filters on the x-axis and 2 on the y-axis, and you can see that the 2 populations they have a split. So this one is sensitive to nitrogen. You can see that it's not just a spread in nitrogen; there's a real bimodality in it. So this is what we naturally get. So then we can also produce a sodium-oxygen anticorrelation. We actually have distributions of sodium and oxygen, and we can now also do that in 2D. So here we have done that for the Caretta catalog, so 16 clusters. I'm not too happy about this. So you can see that the data is really under-predicting, or the models are over-predicting the data. And the reason I said it the other way around is because, like a theorist, I've been trying to find errors in the data. And there are some issues with oxygen and sodium. They're actually difficult abundances, but I'm not going to yet claim that the problem lies with the observations. But if there are people here in the room who are experts in getting oxygen and sodium abundances, I would be very happy to learn more about that. But there are some trends here, but the sodium-oxygen anticorrelation is not so sensitive to temperature. You can see that there are some cases where the data shows very little spread, and the model also shows very little spread, which is encouraging in this one here. But other than that, I think we're mostly a little bit off. We're overestimating the most sodium-rich stars. Magnesium aluminium is better. Here you can see that if you highlight the ones where you have a strong magnesium aluminium spread, our models also tend to show that. Not always as good, like here, a little bit less than here. But it is in the most massive and the metal poor clusters where this is seen, and our model is reproducing that trend nicely, right? So in the clusters that are either lower mass or somewhat metal rich, this is lower mass, this is a bit more, let me see, metal rich one. This one is a bit more metal rich, 47 tux, very massive, but quite metal rich. You see, there's very little spread, and we also find that. So we can reproduce that trend with the mass and with the iron abundance. So then if we look at the photometric result, so here's the spread in helium for individual globular clusters. So every dot here is a cluster, not a star, as I showed earlier. And you can see there's a little trend of the helium spread increasing with mass, which we reproduce. We have also a very strong iron dependence here, or like a trend, which the data don't really show. I'm not sure if that's just noise or our model is over-predicting this trend. And if you look at the fraction of polluted stars as a function of cluster mass, we very nicely reproduce that. I'm not too certain about the vertical offset, could be a bit lower, a bit higher. It is some choice of parameters, but the trend is, I think, robust, and we can really reproduce it. So that's very encouraging. Now, the other thing which is nice is that if you don't fix the gas density in the model, but you fix the iron abundance, and then you do this for different gas densities, you see that you're off, right? So the helium spread in the cluster is telling us something about the gas that it formed from, which is very nice. And it's very sensitive to that. You can see that this is an order or 1.5 dex, and you can see that it's clearly not this one, and probably also not that one. So we can, within a factor of 3, pin down the gas density that globular clusters form from, if you believe the model. So the low helium spread is reproduced, which is the rejuvenation of these accreting stars, which is keeping the helium low. And the specific mass budget is the fact that there's more massive stars in more massive clusters. Now, that's good and well, but now let's, in the final, how long do I still have? 5 minutes, but some predictions. I need to speed up a little bit. So it's quite hard to predict anything solid for the immediate 5 years. I mean, ideally you go out and look for an extremely massive star, but that's still not possible. There might be cases where we can do it with ELT, but what we can do in the short term is look at black holes that might form from these stars, right? So here you see a plot of the remnant mass as a function of the ZAMS mass for different metallicities by Spera and Mappelli. And probably everybody here in the audience is aware that there's a gap predicted between around 50 and 150 solar masses, which is due to pair instability, which happens in massive stars. I'll skip over the details, happy to answer more questions about that, but I think there are experts in the room here that can do that better. So basically what this plot needs to show is that if you had stars above 200-ish solar masses, there should be black holes above 150-ish solar masses, right? So that's the question. Now, we know from the gravitational wave experiments that are ongoing that there are black holes in the gap, right? So there are actually a lot of black holes above 50 solar masses. And the current consensus is, I might be a bit biased in this consensus, but I think it's fair. There's a bunch of papers that have shown that above about 40-ish solar masses, the spins of these black holes seem to go up, and that indicates that they are hierarchical or repeated mergers, right? So there are black holes above 50 solar masses in the pair instability gap, but they don't rule out the fact that there was a pair instability gap because they formed through successive mergers. So in our case, if in our mass function these stars would not make any black holes, then we still have a large range of masses where we expect iMBHs. Some people in literature prefer the term light iMBH because it's not 10 to the 4, but we're talking about a few hundred solar masses. So then at about 12 gigayears, the mass function of the globular cluster contains stars, stellar mass black holes, and then a population of these few hundred solar mass black holes, right? And they're all separated by gaps. I'm actually working with a student on this. The dynamics is very interesting, right? So you have this was very well understood, but now we throw this third family of black holes in, and it behaves very similar with respect to the stellar mass black holes as the black holes to the stars, but having them all three is suddenly not linear anymore. But the question is, should they still be there at 12 gig years, right? This was a stellar evolution plot. But if you leave that move around in the cluster for 12 gig years, are we still expecting them to be there? Well, maybe not, or maybe yes. So if they interact dynamically and they collide and they make a binary that merges eventually, they will get a gravitational wave kick, which can be very high, up to 100 kilometers a second. So in a nuclear cluster, you could retain them, but in a standard 10 to the 5 solar mass cluster, they would be ejected. But then even without the gravitational waves, dynamics would eject them in the same way as massive stars are ejected from a cluster. So you get runaway black holes. And the time scale for this is maybe 100 million years. And you should expect to be able to eject a few percent of the mass of the cluster in massive black holes. But it might be difficult to eject the very last binary black hole of the IMBHs, right? And that is because of this gap. Right? So the parent stability gap makes it hard for the last intermediate mass black hole to be dynamically ejected, because the dynamical ejection is essentially a recoil and by conserving momentum, right? So if your third object is very low mass, the binary gets a very tiny kick. So it's very difficult to throw out the last binary. So maybe. Now, this is something Michele Mappelli pointed out 20 years ago. And we speculated in this paper when we found in the very core of M15 a strange rotation pattern, right? And now I'm like, yeah, this might be a binary intermediate mass black hole. So what's going on here? So this is kinematic, so a rotational signature versus dispersion as a function of distance. And you can see there's a bulk rotation at about the half light radius of the cluster. And then the core also rotates. And Sebastian Kaman has looked at the position angle of these rotation patterns in different shells. And you can see that the core rotates along a different position angle than the rest of the cluster. And this is what Michele in 2005 predicted could happen if you have a massive binary in the center. So the torque of the binary starts to align the stars with the binary. And in this paper, we tried to see, can you do this with a stellar mass binary black hole? And you can't. There's not enough angular momentum. But if there are two 200 solar mass binary black holes, you can do it. Now, the second thing you can try to look for, of course, and it's the final thing I want to say here, is you can look for gravitational wave signals of these very massive binaries, right? So even though they may be ejected upon coalescence, you should still see the merger signal, right? But the masses are quite high. So in the current sensitivity curves of LIGO Virgo, we can see this is the classic first gravitational wave source, which is right in the middle of the sensitivity curve. And the most massive object found up to now is this, sorry, I missed the title here. This is 231123. I copy-paste from the previous slide. I forgot to update title. This is what happens when you do it in the train and you wake up at 4 in the morning. So, but the masses are correct. So this is 130-something plus 100 solar mass binary, right? They spin very rapidly, so I don't think this is a candidate to confirm what I've been saying here. Everybody is now discussing this object. Is it a hierarchical merger, or is it actually lensed, or is it eccentric? There's something else going on, but the masses seem quite robust. But this is already going at the edge of the frequency of the current gravitational wave detectors, right? So we have to wait until the Einstein telescope, and then we can probe this mass regime. The challenge is also that if they merge in globular clusters, this happened at a redshift of 2 or 3, right? So we need to go further, deeper, and at lower frequencies. But I don't think we're multiple. We're not 100 years away. I was saying before, we need to wait 100 years before we can model this globular cluster probably. But I think in 10, 20 years, we can probably see these IMBHs, if they're there. So I'll stop here. So the key point is that these multiple populations, they can naturally be explained if clusters form from dense gas, which makes sense because the early universe was just denser. And if that was due to these extremely massive stars, then we had stars up to 10 to the 4 solar masses, and therefore also IMBHs. And both of these findings are somewhat now constrained by the elemental abundances we see, right? So as we further refine the model and we get better data, we can keep these two in tune, which is very exciting. So the predictions we put forward is that there should be stars above the parent stability gap with low spin, right? So that they are different from the hierarchical mergers that we have already found at the upper end of the parent stability gap. And there might be a single or a binary light IMBH left in several globular clusters because they are difficult to eject. And we may be able to find them in very deep observation, high resolution, with, for example, ELT, if they have captured stellar companions. And I'll stop here. Thank you very much.
Thank you, Mark. Very interesting talk and extremely well explained. Thank you very much for that. We have some time for questions, like 8 minutes or so, but the good news is that Mark is going to be around for a couple of days and you have the opportunity to chat to him.
It's a very nice talk. If you have an IMBH in the middle of a globular cluster, and they're these really massive ones, why don't we see more microlensing events?
Yeah, it's a good question. So people have done the calculation. It's actually extremely difficult to do. It's very rare. So people have done calculations for M22, which is projected onto the bulge, and it's a very massive cluster. It might have, as been argued, might have a 10 to the 4 solar mass black hole. And even for that, the rates are extremely low. So 10 to the 2 or 10 to the 3 solar mass individual black holes is extremely rare. But I'm very happy to think about other ways to find them, because there's hopefully there are.
Yeah, thanks for the lovely talk. 2 quick questions. The first is iron. So I gather that you do not expect these objects to make iron that can be used in the local star formation, or you would have outruled them because most of these don't show spread in iron. And the second question is, can you make a magnesium-potassium anti-correlation in a single one of your most massive stars, or do you, in order to do that, would you need both the most massive stars to make the potassium and then also a population of the lower mass stars in the same cluster to account for the magnesium depletion?
So let me start with the first one. Can you remind me what the question was?
The question was, so you have a constraint on most of these clusters that they have to have the same iron abundance.
Oh, yes, yes.
Which means that you can't have the supernova messing things up.
That's right, that's right.
So for these stars, why is it that the supernova does not produce iron that manifests in the secondary population?
Oh, okay. Yeah, sorry, I may have not explained that well. So there are people who say that direct collapse supernova don't actually produce any iron. I'm not going there, but we're saying most clusters probably form faster than 2 million years. So then there will be supernova, but then all this gas accretion has already stopped. And it might stop because of the supernova, as the feedback. But in our sort of densities, the time scale for the cluster formation is actually 1.5 or 1 million year. So you never have stars that reach the end of their made sequence life. There is an intriguing subcategory of clusters, which are the most massive ones, that start showing other features, like an iron spread. And so these may have actually formed longer than 2.5 million years, so then you start to see, perhaps, these iron spread discussions are very wild, because people look at different lines and different methods, and they get iron spreads or not. So I'm not yet convinced we actually have seen iron spread, but there are clear cases. Omega Cen has an iron spread. There's maybe 10 different populations in Omega Cen, but that's probably a former nuclear cluster that had undergone multiple starbursts, perhaps. There's other things that could have been going on. But the 10% subset that shows interesting results also shows products of helium burning. That's nice, right? If helium burning and supernovas are very close together, so if there are iron spreads and maybe helium burning products, C plus M plus O starts to go up, maybe that indicates that these clusters took longer to form. Now, potassium. Thank you. I like potassium. So sure. Potassium-magnesium anticorrelation is what you get at very high temperatures.
Okay.
But what's observed is a potassium-sodium correlation. And that's not what you expect at very high temperatures, because above 80 million Kelvin, all the sodium is depleted. So you actually expect at high potassium, you expect low sodium. So I'm working on this now. Of course, these nucleosynthesis calculations at a fixed temperature are oversimplified, right? If you have a star which has 100 million Kelvin in the center, it has an envelope which is 40 million Kelvin, right? So maybe you make sodium in the envelope, and you mix it with this depleted sodium material. I don't know the answer yet. But the magnesium, potassium anticorrelation, that's what you expect at very high temperature, and that's observed. People see very magnesium depleted stars which are potassium enriched.
Okay. Yeah, I can't remember what the sodium did, but I know there's a cluster NGC 2419 that shows exactly that magnesium potassium. But
just going to show it.
It's been
Potassium here, yes. Yeah, sorry, I actually don't have the potassium plots here, but I made a summary of the clusters that show it. There's a bunch of them. And I'm not sure yet that the others don't have it because we haven't looked, or they don't have it. But what's intriguing about the ones that show it, they're very extreme clusters, right? Omega Cen, M54, this is currently in the center of Sagittarius dwarf. 2419, the one you mentioned, that's a very clear case. It's also been proposed to be former nucleus of a satellite that came in together with the Sagittarius dwarf. This one, I don't think, this is a clear case, and this one too, but they don't seem to be nuclei of galaxies, at least not, they have not been proposed. And M15, there's a little hint, which is also interesting. So it's very rare. This is really the only ones that I could find in literature. But they require these kind of temperatures here, and then you're really talking about 10 to the 4 solar masses. So I've been working on these supermassive stars 6 years ago, and everyone said, you're crazy. So now I went back to the 10 to the 3 solar mass, and people say, yeah, it might be, but how do you make potassium then? Yeah, well, now we need these 10 to the 4 solar mass things, maybe.
I guess it's nice that it's rare, because if these most massive ones are rare, then you've naturally explained why you only sometimes see it.
Yeah, that's right. And the other thing, which is we've written in the paper a section why this cannot be the case in every globular cluster, because these things may leave behind very massive intermediate mass black holes, and that would be a problem because clearly we haven't found them apart from Omega Cen, perhaps.
Okay. Hi, Mark. Amazing talk. I have like many questions, not about. Yeah, but yes, exactly one. Not about the things that you said, but things you did not say.
Oh, okay.
So, for example, you very nicely explained that how with this model for extremely massive star formation, you can explain, like if you scale it up to globular cluster, and you like explain a lot, very good. But there are also other consequences. For example, one of the things is you do not see these multiple population in really young clusters. Can the model explain that as well? Also, at the moment, you are considering everything in like an isolated box, kind of. So for example, you consider only like early evolution and you say, we have explained everything. But the thing is, we are seeing these clusters now, right? So can you also like explain that these patterns, these abundances that you have seen will survive further evolution of stars, and also the best part, dynamics of cluster. Can we explain that as well?
Okay, let's start with the young clusters. Yeah, that's a really good point. So it's not that we don't see it. We've seen nitrogen spreads down to ages of 1.5 gigayears in the LMC and the SMC. We is royal we, yeah? It's people working on HST data of, and some sodium oxygen anticorrelation, I believe, as well in a 2 or 3 gigayear cluster. So I would say that's quite young already.
Yeah, I mean, I think it's like the boundary is like 2 gigayear or something, with maybe a couple of exceptions.
Yeah, now there was a few years there were people saying there's a very sharp boundary, like at 1.5 gigayears exactly. And people started to say, oh, it's an internal stellar evolution effect because something changes at 1.5. I forgot the details. But that seems to have gone now. So it seems that the strength of the signal really goes down with decreasing age. And at some point, it just becomes undetectable, but it's not clear whether there were no stars. I mean, we know that there's a 300 solar mass star in R126, which is 1 million year old, right? So it's very high in sodium. So if that wind ends up in some low mass stars, it should be nitrogen enhanced. It's favored in the lower metallicity cases to see all the other things. So it's harder to make the sodium and the aluminium at lower metallicity and at lower alpha abundance. So if your alpha abundances are lower, you have less oxygen, sorry, you have less neon, of which you make sodium, and you have less magnesium, of which you make aluminium. Right, so at redshift 0, alpha is over iron is 0, and so you have 3 times less material to make the sodium and the aluminium. That's one thing, and the iron abundance also makes all the reactions slower. So it takes more time to reach the maximum sodium and the maximum aluminium, but you can still make nitrogen. So actually nitrogen should still be there, and it is also expected that nitrogen without sodium should be seen. So the other question, that was maybe something for a future discussion, because
Yes, maybe we can talk
I'm
later.
happy to chat more about that.
Yeah, I think there are many more questions from people actually, but we are a few minutes past 12 already. So I encourage people, including cosmologists in the room, to go and talk to Mark after the seminar. And for now, let's thank Mark again.
Thank you. You're welcome.
And I hope to see you guys all next week for the seminar by Anna Chiara, I believe. Uk wants to say something.
Yeah, so Mark is here till tomorrow early afternoon, so if you still want a slot for discussion, Kunal is coordinating this, so reserve Mark's time, it's precious. And second, we're going to the Zorba tonight, and I think we've still room for one person. No, it's full? All right, too bad.